Is she actually coming?
She said probably. I mean, she's been saying probably all week.
Right, but what does probably even mean in this context? Are we talking like a 60% chance? 75? Because it completely changes whether I need to buy more snacks.
Well, we make calls like that all day long. You look at the sky to decide whether to bring an umbrella, or you check the time to guess whether the bus will actually be on schedule. Every single one of those decisions is you just gut feeling a chance.
Yeah, and that text you just got, that gut feeling percentage, that is exactly what we are evaluating in week 1 of this introductory probability course. The goal here is taking those vague, everyday probablities and forcing them into a strict mathematical rulebook.
Right, we are looking at the foundational language you need before you can calculate anything.
And looking at the notes, the first thing the syllabus does is draw this massive line down the center of the material. There are 2 distinct halves you deal with in this field: probability versus statistics.
Exactly. Before we do any actual math, we have to know which side of the line we are standing on.
I always try to visualize this, like walking into a casino. Probability is having the casino's blueprint. You have the rule book wide open. You know exactly how many decks are in the shoe. You know the roulette wheel is perfectly balanced. And you use that mechanical knowledge to predict the score.
I like that analogy.
But statistics is walking onto the casino floor completely blind, and you are trying to write the rule book just by watching people lose money.
Yeah, that framing focuses perfectly on the direction of your logic. Because probability is forward reasoning. You start with the known mechanics of a system.
Right.
So because you know the coin in your pocket is perfectly fair, you can confidently predict the likelihood of different outcomes before you ever flip it.
I know the rules, so I predict the outcome.
Exactly. Statistics, on the other hand, is backward reasoning. You don't know anything about the coin, but you observe a friend flipping it 7 times and they get 5 heads. In statistics, you take those observed outcomes and work backward to ask, well, is this coin actually fair or is it weighted?
Outcomes to rules. Okay, that makes sense. And looking at the material, everything we are covering today sits squarely in the probability half. We are entirely focused on forward reasoning.
We know the rules of the game.
Yes. So since we are doing forward reasoning, we have to establish the scale we are working with. When we assign a number to an event, probabilities always live strictly between 0 and 1.
Right, with 0 meaning the event is strictly impossible, and 1 meaning the event is absolutely certain.
But everything you actually have to weigh in life lives in that gray zone between 0 and 1, right?
Right.
If you have that perfectly fair coin, the probability of heads is 1/2, and the probability of tails is 1/2.
Yeah, but if we bring in an unfair coin weighted differently, maybe the probability of heads is 2/3 and tails is 1/3. And we should probably point out a really common trap here.
Oh, because people misinterpret what that number means in reality.
Exactly. If an unfair coin has a probability of 0.66 for heads, that does not guarantee you will get exactly 2 heads every time you flip it 3 times.
Right. Probability is a likelihood, not a promise.
Yes. It tells you what is mathematically sensible to expect over a long-term average. It dictates the long game, but it has absolutely no control over short-term reality. A 66% chance just means the mechanics lean in that direction. It never guarantees the physical outcome of the next 3 individual flips.
And this scale applies to continuous scenarios too, right? Not just discrete coin flips. For example, predicting the probability that the winter temperature falls within a specific 10-degree range. That likelihood is still just a single number living somewhere between 0 and 1.
Right. But to talk about those likelihoods with any real precision, we can't just wave our hands and say heads or cold weather.
Yeah.
We have to define exactly what is happening mathematically.
Which requires a specific grammar.
Exactly, the language of sets. Sets form the grammatical foundation of everything in probability.
Okay, so a set is simply a collection of things. We call those things elements. Looking at the notes, there are 2 main ways to establish them. First, you can literally just list the elements out. Like if you were picking at a grocery bag, you could write a set containing an apple, an orange, and a banana.
Or, if the set is too large to realistically list, you state a condition.
Right.
So you could define a set as all registered voters in a city. You aren't naming them individually, but the rule gives you a strict boundary of what belongs inside the set and what doesn't.
The notation here matters too, because reading the math aloud correctly is the first step to internalizing it. When you are looking at a set, let's call it capital S, and you see vertical bars around the letter S, you must read that aloud as the size of S.
Yeah, it is simply a count of the inventory. If your set is the grocery bag with the apple, the orange, and the banana, the size of S is 3.
Okay, we also need to review a few foundational number sets that dictate the boundaries of our math. We have the natural numbers, which are your counting numbers. 1, 2, 3, and so on.
Then the integers, which expand the boundaries to include 0 and the negatives.
The rationals, which are your fractions, and the reals, which fill in every possible decimal gap.
And just as importantly, we need a specific name for a set that contains absolutely nothing. When you see a circle with a diagonal slash through it, you read that aloud as the empty set.
It always feels a bit, I don't know, abstract to name a container that holds nothing. I mean, why do we need a formal symbol for an empty grocery bag?
For the exact same reason we need the number 0 in standard arithmetic. You have to have a structural placeholder to represent that nothing happened or that no overlap exists. Without the empty set, the logic of probability equations would completely break down.
Okay, so we take this grammatical set language and we apply it to what the course calls a random experiment. A random experiment is any process where the outcome isn't predetermined.
Right, and when we run one of these experiments, we map out everything that could possibly happen. This forms our sample space.
The sample space is always written as a capital S.
Yes, it is the entire universe of all possible outcomes for that specific random experiment.
So S equals the set containing all the possibilities. And an event is simply a subset of S. It's a specific slice of that universe.
Exactly. Let's map out a random experiment of flipping a coin twice.
Okay. If I flip a coin twice, my sample space S equals the set containing HH, HT, TH, and TT. 4 possible outcomes. So the size of S is 4.
Now we define a specific event within that universe. Let's call event E getting at least one head.
I look at my universe, and the subset that matches at least one head is the set containing HH, HT, and TH. So 3 outcomes.
Now define another event F as getting no heads.
That subset only has one valid outcome, the set containing TT.
And the standard way to map this out visually is a tree diagram.
Oh, right. You start at a single point, draw 2 branches for the first flip, heads and tails. And from each of those branch ends, you draw 2 more branches for the second flip. The final leaves to the very end of those branches give you your complete sample space. I want to look at the next scenario in the notes, because the random experiment gets a bit strange. You flip a coin. If it lands heads, you flip the coin again. But if it lands tails, you stop flipping coins and instead roll a standard 6-sided die.
This is an uneven branching experiment.
Right. If I draw that tree diagram, it is going to look entirely lopsided. The heads path splits into just 2 branches, but the tails path suddenly splits into 6 different branches. Does it cause a mathematical problem that the paths to get to the outcomes are completely different lengths?
The differing path lengths are completely irrelevant to defining the sample space. The sample space only cares about the final resting places.
The leaves.
Exactly, the final leaves on the tree, regardless of how many mechanical steps it took to reach them.
So my sample space S equals the set containing HH, HT, and then T1, T2, T3, T4, T5, and T6.
So the size of S is 8. You just count the 8 final leaves on that tree.
Okay, mapping with trees is straightforward. When we have discrete, countable outcomes, like coins and dice, you can literally point to the branches. But the real world isn't always neatly divided into distinct steps.
No, it rarely is.
So if we're going to define a universe of outcomes, that tree diagram strategy falls apart completely the second we look at something continuous.
Right. You cannot draw a tree diagram for an infinite number of outcomes.
Yeah.
We have to shift to continuous sample spaces, where outcomes are numbers falling somewhere along an unbroken line.
The pedagogical illustration in the material uses temperature. Let's say the winter temperature in a specific city varies anywhere between 10 degrees and 100 degrees Fahrenheit. The sample space isn't just 10, 11, 12.
Right.
It's every possible fraction and microscopic decimal in between.
Yeah, SES is that entire real number interval.
And the shift from discrete points to a continuous interval introduces a new physical reality. The probability of landing on one exact, infinitely precise decimal point is functionally 0. Wait, let's break that down because that sounds confusing. Why is the probability 0 if the temperature obviously has to be something?
Because you are dividing by infinity. In a discrete space, the chance of rolling a 3 on a die is 1 out of 6.
Right.
But in a continuous space, the chance that the temperature is exactly 50.0000 with infinite zeros is one out of an infinite number of possible decimals. That's why we don't calculate the probability of exact points anymore. We have to calculate the probability of falling within a range.
Which is why the notation regarding the boundaries of that range is so critical. You have to specify what happens exactly at the border. We use brackets and parentheses.
Yes, let's walk through the closed interval from 10 to 100.
Okay. Our sample space S is the closed interval from 10 to 100. That means 10 degrees is physically possible, and 100 degrees is physically possible.
Right. Now let's define an event E as the reading is below 50 degrees. Event E starts at the bottom of our universe, which is 10. We place a square bracket next to the 10.
Because the bracket means the endpoint is strictly included in the set.
Exactly. But the upper boundary of our event is below 50 degrees. It does not include hitting 50 on the dot. So we write 50, but we place a round parenthesis next to it.
So the event is 10 up to, but not including 50. Bracket included, parenthesis excluded.
Yeah.
Feels like a tiny grammatical nitpick, But if you put a bracket on the 50 instead of a parenthesis, you are mathematically defining the wrong event. You're including an outcome that violates the rule below 50.
Exactly. You are telling the equation that exactly 50 is a valid success state, which alters the boundaries of the integration you'll eventually do later in the course.
All right, so we have our universe mapped. We know how to define sets, whether the experiment is discrete or continuous. Now we need to start combining different events together. We introduce mathematical operations.
Right, and we begin with union and intersection.
Okay, so the union. This is the OR operation. It means an outcome is in A, or it is in B, or it happens to be in both. I always used to mess up union and intersection, honestly. The only way I remember it is visual. The union symbol opens upward like a cup.
Right, it's catching everything.
It's the OR operation, so it casts a wider net.
Just remember, the pronunciation rule here is strict. You must read that symbol aloud as probability of A or B.
Right. Then there is intersection. This is the AND operation. The symbol opens downward. It looks like a little pitched roof, covering only the narrow specific spot where the two events cross paths.
Because it's the AND operation, so it's restrictive, just the overlap.
And you read that aloud as probability of A and B.
Yeah.
So union is the combined total footprint. Intersection is just the strict shared overlap.
We also have the complement. If you have an event A, the complement is everything in the sample space S that is strictly not in A.
And you read it as A complement. Usually has a little C superscript next to the A.
Right. So if your random experiment is rolling a die and A is rolling an even number, A complement is rolling an odd number.
Next is the difference operation, written with a backward slash. You read it aloud as A\B. It means outcomes that are in A, but strictly not in B.
It's a subtraction of overlap. You take event A and you carve away any part of it that happens to bleed into event B.
The notes bring up De Morgan's laws here as a way to translate between these operations. They state that the complement of a union becomes an intersection of complements, and vice versa.
Right. It distributes the not concept across the expression.
So it is incredibly useful because it allows you to bypass messy calculations. Sometimes calculating A or B requires a lot of complex addition and subtracting overlaps.
Let's look at the actual translation. A complement of a union, so the opposite of A or B, becomes an intersection of complements, so not A and not B.
Think about the weather. If I want to find the probability that it rains or snows today, calculating that union might be frustrating.
Right, you have to calculate the rain chance, calculate the snow chance, and subtract the chance they both happen so you don't double count.
It's a lot of separate pieces to track.
But De Morgan's laws give you an alternative. The opposite of rains or snows is does not rain and does not snow. It might be vastly simpler to just calculate the probability of a perfectly clear day and then subtract that single number from 1.
Oh, De Morgan's laws let you flip the equation to whichever side is easier to solve. That makes the math so much more agile.
It really does.
Now, combining these events leads directly into what is arguably the single biggest conceptual trap in this entire week of material. Students constantly confuse two distinct concepts, mutually exclusive and complement.
Yeah, this requires unhurried attention. Let's define mutually exclusive first. Two events are mutually exclusive when their intersection is the empty set.
Meaning they share absolutely no outcomes, they can't happen at the same time?
Exactly. Let's use a standard die roll. Event A is getting a 2, event B is getting a 3. You cannot roll a 2 and a 3 simultaneously on a single die. The overlap is the empty set. So rolling a 2 and rolling a 3 are mutually exclusive.
Now compare that to a complement. A complement requires two conditions. First, there is no overlap, meaning they are mutually exclusive. Second, together, They must perfectly cover the entire sample space S.
So walk me through exactly why students merge these two definitions in their heads using that same die roll.
Well, a student will look at event A rolling a 2 and event B rolling a 3. They recognize that a 2 and a 3 cannot happen at the same time, so they correctly identify the mutually exclusive nature of the events.
Right.
Then they incorrectly assume that makes 3 the complement of 2.
Because not a 2 feels like it should just be another singular specific number. They treat complement as a synonym for alternative.
But look at the strict definition of a complement. The complement of rolling a 2 is everything else in the universe of outcomes. It is the set containing 1, 3, 4, 5, and 6. It is absolutely not just the set containing 3.
So a 2 and a 3 are mutually exclusive, but 3 is not the complement of 2. Every single complement pair in existence is mutually exclusive because they cannot overlap.
Right.
But not every mutually exclusive pair is a complement because they might not cover the whole universe.
That distinction is the one that causes the most red ink on exams. Mutually exclusive simply means they don't touch. Complement means they don't touch. And together they assemble the entire universe.
Yeah, and trying to hold all these intersections, unions, and complements in your head simultaneously gets overwhelming, especially when you introduce a third event. This is why the visual aids are so important.
Like the Venn diagram.
Exactly. You draw a large rectangle to represent your sample space S, and inside it, you draw overlapping circles for your events.
When you draw a 3-circle Venn diagram, so circles A, B, and C overlapping in the center, it physically divides the space into 7 distinct numbered regions, plus the empty space outside the circles.
Thinking of sets as physical areas replaces the need to memorize dense algebraic formulas. Let's use a coffee shop order to anchor the visual. Circle A represents drinks containing espresso. Circle B represents drinks containing milk. Circle C represents drinks served iced.
Okay, 3 overlapping circles, espresso, milk, iced.
If you need to find the expression A or C, you don't calculate an equation, you look at the visual boundaries. You simply shade in every single region that is inside the espresso circle, plus every region that is inside the ice circle. You just combine regions 1, 2, 3, 4, 5, and 7.
And what if the expression asks for probability of A and B and C?
Well, you are looking for an intersection, the ice in operation. So you trace the area where all 3 circles physically cross over each other.
In our coffee shop, that's a drink that has espresso and milk and is iced, an iced latte.
Right.
If you look at the diagram, that is just region 1, the dead center of the overlap.
Visualizing these problems spatially is a really powerful habit. It takes abstract vocabulary and grounds it into geography. You trace the map instead of parsing the algebra.
So we set out to establish the ground rules of probability. And we have the language mapped. We separated forward reasoning from backward reasoning. We defined sample spaces as the universe of outcomes. We defined events as subsets.
And we walked through the set operations: union, intersection, complement, and difference.
We also examined the notation for discrete sets versus continuous boundaries. And we clarified the strict, unforgiving difference between mutually exclusive events and complementary events.
Right, and all of this set building perfectly positions the logic for the next lecture. Once you can accurately describe an event as a specific subset, the very next natural problem to solve is figuring out how many outcomes are actually sitting inside that subset.
Because if your sample space S equals a set containing thousands of outcomes, you cannot draw a massive tree diagram. You would literally run out of paper.
Exactly. So the next lecture shifts entirely to counting techniques. We will look at multiplication rules for massive branching paths, permutations for when the order of outcomes matters, combinations for when the order doesn't matter, factorials, and multinomials.
Counting mathematically is the engine that actually drives the probability calculations. We've built the grammar today, and next time we give it some actual horsepower. But it really leaves you with something to think about. If mapping the probability of simple coin flips and die rolls requires this much strict vocabulary, how does this mathematical foundation scale when scientists model millions of interacting random events in nature, like weather systems or genetics?
That's the real challenge.
Until next time.